Good morning. So, we will continue with the clutch design. Yesterday, we have discussed the basic things, clutch types and also the working method of clutch. And today, we are going to learn about the torque transmitting capacity, how much torque when clutch is engaged transmitting during the engagement. Within that, we will discuss about uniform pressure theory. Using that, what would be the torque and also uniform wear theory. Okay. See, as I said, the difference between a brake and a clutch are similar, they are not very different. Okay. Particularly with respect to clutch, within the brake, I am talking about disc brake. In the disc brake, you have an annular pad, either it will be annular pad or circular pad through caliper attachment. The same thing, if you extend it as a full size, right, that become your clutch. That is the difference. So, the functionality is also same. The purpose is to hold in clutch aspect, whereas to stop in brake aspect. That is a difference. Yeah. So, now we will try to find out how the torque going to be transmitted during the engagement. Okay. So, I have just taken the simple single plate clutch. This is single plate. Yeah. The single plate clutch, where you can see this is the inner diameter and this is your outer diameter. In between, you have a friction lining. So, this entire thing is a friction lining. It is exaggerated, but for our understanding, we made it as a this is your contact area, surface contact area or as friction area, entire thing on the pad. Okay. And this is the side view, you could see that, and then you would have seen the video, and also I have shown the model. You have diaphragm, right. When you engage, they will give you a force, right. The force will give you to make a contact. So, through the pressure plate, you will have reaction forces, right. The as a pressure along the this area, entire area, the pressure is developed. It has to be balanced. Okay. This is the one. So, we are going to take a small strip, as you see the complete this is the small strip with the dr thickness from the radius r, okay, from the center, and we will see what exactly is going to be happen. And where your P is your force, small p is the pressure intensity, okay, acting along the friction lining, yeah, friction lining surface. And if you look at, so we need to understand how the torque will be transferred. Before that, I try to get the basic equation for the force aspect. So, in the elemental area, the force normally would be the intensity pressure with the circumference. Okay. So, you can see P into 2 pi r dr, that is elemental axial force. Same thing, if it is a frictional force, you have to multiply with your coefficient of friction. So, mu is your coefficient of friction of friction lining, right, coefficient of friction lining. Yeah. So, that is the one is helping to transfer the torque through frictional arrangement. Now, the frictional torque would be obviously the frictional force into distance, which is r, small r. Okay. So, and in this we are assuming that the coefficient of friction is constant, it is not variable with the temperature, and pi also constant, only the variable would be p r square and dr element things. Okay. Now, we want to see the basic equation for the load aspect. Between the limits small d by 2 capital D by d p r dr. Similar way for torque basic equation, right, frictional torque will be 2 pi into mu, the same thing except you have a one more r, that is it. Okay. This two equation, this is the basic equation before going to uniform pressure theory and uniform wear theory aspect. Okay. Yeah. Just note down these two equations, please, for the total load acting on the clutch and the corresponding torque also. Yeah, right. To design parameter, as I said, capital D is the outer diameter of the friction disc, small d is the inner diameter of the friction disc, P is the pressure intensity of pressure at radius r, and P is the total operating force, T is the torque transmitted by the clutch, and mu is the coefficient of friction of friction lining material. Okay. Now we will discuss, as we did in disc brake. So there are two theories used in clutch. One is uniform pressure theory, other one is uniform wear theory. So okay, when the clutch is brand new, okay, so when they made a contact, right, the contact is uniform. When you have a contact, uniform contact, the pressure will be uniform. Okay, that's why it's called uniform pressure theory. You may ask why we have to follow two different theories, right? I'll explain as we proceed in the lecture. And when you new clutches employing a number of springs, the pressure remains constant over the entire surface area of the friction force. So okay, then what is happening to the torque things? Okay, so that's what we are going to do that. So we need to find out the load, right? So the basic equation we know that load 2 pi r, okay, or dr. This is the equation we have. So then we substitute limit, right? It's a basic integration r square by 2. So put the limit d by 2 and small d by 2. I'll straight away go for the equation. Then P would be the acting load. So this is the capital P is the load, please, and this small p is the pressure intensity. Yeah, please understand that. D square small d square. Okay, this is the equation. This is the equation for the acting load. Maybe you can have equation number 1. Now we need to find out for the torque also. Okay, torque equation we know, right? Torque equation T equal to same thing, right? It's a frictional torque. Yeah, 2 pi mu small p, right? D by 2 by capital D r square dr. Okay, this is the equation. So when you again integrate and substitute the limits, finally I am going to give an answer. The torque would be pi mu p by 12. Okay, so we'll have a d cube and small d cube. So this is the equation torque. Right. Maybe we can take it as equation 2, but already we know that the P equal to what from equation 1. The actuation force P equal to this is the equation, right? This is the equation 1, right? So you can substitute, just I want to replace the pressure intensity, right, and try to bring everything with respect to load. Okay, so when you do that, finally you would expect your torque equation mu capital P by 3. Okay, yeah, d cube small d cube d square and small d square. So this is the equation we are expecting. So in fact the same we did the same equation we arrived at when we did for the disc brake system, right? So mu, right, P is the load, as the entire thing I am talking about this this entire thing we take it as a RF. RF is nothing but frictional radius. Okay, this is RF equal to frictional radius, which is nothing but d cube, right, small d cube 3 d square and this small d square. So this is the value. So this would be vary again for uniform wear theory also, try to understand that. Okay, so this is for the uniform pressure theory, already we got equation. So this you can make it as a equation number 3 also, yeah, as a 3. Yes. Now, uniform wear theory. So, this is for the uniform pressure theory. Okay. So, what do you understand the uniform wear theory? Why there is a uniform wear theory concept in clutch thing? Okay. The same concept, you have a we take the D is the inner diameter and the capital D is the outer diameter, right. This entire portion would be friction lining force, right, the surface area. So, the wear is uniform when the pressure is not uniform. This is usually applied to worn out surface, okay, worn out surfaces, okay, on the clutches. When do you expect the uniform wear? That is the question. So, when the clutch is brand new, so the surface is very smooth and nice. So, when they make contact, the pressure is uniform. So, over the time period, so they have to stick and again they will rub each other, because the frictional thing, right, they want to hold it. So, because of that there will be a wear is happening. So, when the wear is happening, so some places we have a wear, other places we may not have it. So, what happened to the contact? The contact will not be uniform. Okay. So, when the contact will not be uniform, the pressure cannot be constant. So, the wear is taking place, right, that is why, and again this will continue as until the surface is wearing out through the frictional surfaces to make it as a uniform wear theory. We will go one by one, and the same similar to what we did with uniform pressure, the same way you can do that. Only difference is, what is the difference here? What do you expect the pressure aspect? There uniform pressure theory, the pressure is uniform, but here it can't be. Okay. The pressure would be more at the inner radius. Obviously, the smaller radius pressure will be things. So, you will have nice parabolic, you could see that. So, this is a pressure intensity. Yeah. So, at the inner you will have a more pressure, at the outer you will have a less pressure. So, that is a thing, and generally we say as a PA, maximum allowable pressure intensity. Okay. PA is the probably you can put this as PA is the maximum allowable pressure intensity, small PA please. Pressure intensity. Okay. So, already we have basic equation, from there we are going to proceed. Before that, try to understand. Okay. So, where is proportional to the friction force? Okay. Have you heard about Archimedes equation? Anybody? Archimedes equation, right? So, the higher the velocity, the right, the wearing of the more will be, right. The more the force, again the wear will be more, right. So, obviously, the wear is proportional to your frictional force and the rubbing velocity, right. So, this is your frictional force, this is your velocity, rubbing velocity. Usually, we say a sliding velocity V equal to R omega, right. So, you can have a R 2 pi n, when you can take it as a RPM or RPS, either way is fine. So, we have take it as a RPM. Then, when the coefficient of friction speeds are constant, what happened to your wear? My friction is constant, okay, and speed are constant. So, what do you expect the wear will be? Wear will be constant, right? The wear will, because of no variables. The P is constant, your mu also constant. So, there will be proportional, wear is proportional to the mu r. But this is okay when the wear is uniform. This is what happening. But in actual contact, okay, the pressure variation will be there, right? When the pressure variation is there, so the pressure intensity is maximum at the inner diameter. So, obviously, what do you expect? This PR would be proportional to your P allowable into d by 2 at the inner radius. Yeah, at inner radius. Okay. Please understand this difference between the uniform wear theory and pressure theory. Now, we will do the, as usual, the load aspect. The only difference is PA will come into the picture. P equal to pi, same equation. Yeah, d by 2, right, small pr and dr. So, that will replace 2 pi, right. we can have PA allowable, right? PA d by 2, okay, then dr. So, okay. So, once substitute and do the integration, finally, I am going to give the equation straight away. Your activation force will be PA, okay, d by 2. So, this is the equation. Maybe you can take it as a equation number 4. Similarly, for torque, T equal to 2 pi mu. This is your standard equation, right? Yes. So, substitute the this here. 2 pi mu is the constant, whereas the variable will be PA. I am just replacing P, right? PA into d by 2. Then you have a R square. Right. I think no, I should be R only, not R dr. So, when you substitute, you would expect the equation T equal to pi mu PA, right, d by 8 d square, small d square. This is equation number, you can say as a 5. So, already we know equation number 4. From there, if you take it, right, and substitute for the PA aspect, you would expect the equation torque equal to mu P by 4 d plus d. So, this is the equation expect. Equation number 6. Okay. If you standardize, T equal to mu, right, P RF, where RF equal to plus capital D by small d by 4. Okay. Remember, there you have a d cube minus small d cube, right, divided by 3 into d square by minus d square. So, that is the difference. Frictional radius will be different. Yeah. So, this is for the uniform pressure theory. Okay. This is for uniform pressure theory. Now, yeah. So, I think again this is the same equation what I have written is coming here. Yeah, that is okay. Right. So, now I am going to give a concept, little bit concept. Since the wear is proposed to the radius, the wear at the outer radius will be more, right, PR, right. So, obviously, wear will be more. So, the Ag will be, the wear will release the pressure at the outer radius. This will continue until you remove this the wear material. So, what happened? Because of that, again the contact will be uneven, right. The pressure will shift to the inner radius, right, the inner radius will start to wearing out. So, no further wear at outer edge, but wear will now take place at inner edge due to the contact pressure of the plate. So, this will release the pressure and stop further wear at the inner edge. This is what going to happen. So, this will continue until you will have a uniform wear through the surface, contact surfaces. That is why this is called as a uniform wear theory. This process of wear mechanism continues alternatively at inner and outer edges until PR is a constant, resulting uniform wear theory at any given radius. So, this is what happened. Okay. In fact, what are the factors will affect the torque capacity? So, decreasing the diameter reduce the torque capacity, that is one aspect. The second is a smaller diameter clutch has a smaller diaphragm, which will give you lower clamping force. So, when you have a clamping force, again you can't do the desired function. Okay, that is another disadvantage if you have a smaller. So, adding a second clutch disc double the torque capacity. Obviously, your number of rubbing surfaces will be increased, right. So, the same concept is applicable multi disc clutch aspect. Increasing the coefficient of friction obviously of the clutch disc increase the torque capacity. If the multi-disc clutch is correctly designed and engineered, the losses from the smaller diameter and lower clamp force are much less than the the gain in coefficient of friction and extra disc, giving the torque increases. Understand please, okay. So, better if you have a higher coefficient of friction and more disc, or that means more frictional surfaces, that will contribute increasing your torque capacity. Right. So, now I am going to give us a little bit scenario. So, this is the general equation, right, where this is already we know that, and this is for the uniform wear theory, both I have given. Now, I am giving smaller values, okay. So, just give you capital D 140 and 80 and try to find out what will be RF using uniform pressure theory, and this is uniform wear theory, and this is 56.36 and 55 and 200 outer dia, 100 is the inner dia, my RF 77.78 and 75 for the uniform wear theory. So on, if you do for 200 and 180, I am reducing the gap also, 95 for 0.09 under uniform pressure theory, 95 for under uniform wear theory, okay. What is your observation? What do you see? Do you find any difference between uniform wear theory and uniform pressure theory with respect to frictional radius or effective radius? There is a small increase for uniform pressure theory, okay. There are small incremental things, okay. How about torque? Which one you would expect more torque? Is it under uniform pressure theory or uniform wear theory? That is a question. Uniform pressure theory will give you maximum torque, okay. So, obviously, uniform wear theory will have a lesser torque, okay. So, as a design engineer, which is the safest one? Is it uniform pressure theory or uniform wear theory? So, look at uniform pressure theory has a maximum torque, while uniform wear theory have a less torque, okay. So, already you fix the maximum torque, okay, for when the brand new. As progressing, due to wear, the torque is reduced. When you have a smaller torque, will you be able to perform the desired function? That is the question. Is it possible? My required torque is assuming that 50 Newton, but that is the design torque, okay, operating torque, whereas generating in the contact is a 45 Newton meter. So, in that case, do you able to do you expect that the clutch would perform its duty? Yes or no? No, it is not possible, okay. So, what is that way? So, as a design engineer, we always design a clutch based on the uniform wear theory, not the uniform pressure theory. That's how we do that, okay. And one more thing is, so now we have seen by varying the inner dia and outer dia, okay, but there is a relationship when you want to have a good or maximum torque transfer. So, there is a way to do that. So, normally better to follow the d/d ratio between 1.2 to 2 times. If you do that, so you are able to achieve, in fact, precisely the d/d ratio would come for a maximum torque is 1.77, but you can vary, okay, 1.5 to 2, right. So, in fact, we are going to use this concept while designing a clutch, okay, we are going to do that. So, one more thing is, so this is what I was saying, when the friction lining new, uniform pressure theory is applicable, where is proportional to the radius of clutch, okay. The life of friction lining comes under uniform wear theory, right, based on the friction lining only, other than that nothing can be done. So, obviously, for designing clutches in terms of safe and logical aspect, uniform wear theory is more reliable than the uniform pressure theory, yeah. So, one more information I would like to give is about the rated aspect. Okay, when the design torque is given by Td by Ks and Tr, where K is the service factor or friction margin factor, it accounts for any slippage during the transmission, and TR is the rated torque to be transmitted, and TD is the torque capacity of the design purpose. Okay. So, always better to in the operation, normally this is what you are going to have it. Okay. Better to multiply certain factors such a way that you can have a safe torque. So, that is a practice we have to follow during the clutch design. Okay. Now, we will do a problem, please. Yeah, please take down the problem. An automotive plate clutch consists of two pair of contacting surfaces with asbestos friction lining. The maximum engine torque is 250 Newton meter and the coefficient of friction is 0.35. So, torque 250 Newton meter and coefficient of friction is 0.35. The inner and outer diameters of friction lining are 175 and 250 millimeter respectively. The clamping force is provided by the 9 springs, each compressed by 5 millimeter to give a force of 800 Newton, which is the P, okay, when the clutch is brand new. When the clutch is brand new. So, what should we do? What is the factor of safety with respect to slippage when the clutch is brand new? That is a question number A. The same thing, what is the factor of safety with respect to slippage after initial wear is occurred, which is for uniform wear theory aspect. Then in C, how much of wear of friction lining can take place before the clutch will slip. Okay. What do you mean by understand slip? What do you mean by slip? What is the meaning of clutch first of all? Literal English meaning. Clutch means hold together, right? Clutch means to hold, that is a thing. Slip means you can't hold, it is opposite of that. So, when you that is what. So, the moment remember in the video we have mentioned that, so during the engagement the diaphragm will give you maximum of the clearance is 1 mm, right, that is what is given. The gap between during the engagement disengagement between the friction lining and your pressure plate gap is 1 mm. Okay. If friction lining is wearing out more, what happened to your clamping force? Right, will decrease. Okay. When the decrease is, though the stiffness is constant, because of the force decreases, you cannot extend it. Already the some portion is worn out. So, would you expect to make a contact? No, then you will have slip. So, at what condition you are going to have a slip? That is what the clear given. So, how much need to be wear out? And yesterday I have shown the model also, right. What is the typical thickness of the friction lining did you observe? Is it in few millimeter, 5 millimeter or 6 or 7, that is it, not more than that. So, it is a very small thickness, but of course, it will be there on the both sides. Yeah. Okay. So, now we will solve the problem. Okay. Remember, it is a two pair of contact surfaces, not the one, there are two contact surfaces given, which gives 250 Newton meter. Yeah. So, torque is given 250 Newton meter. Okay. What is the coefficient of friction? Mu equal to 0.35. Yeah. And the outer dia 250 millimeter or else 0.25 meter, you can say that. Inner dia, okay, 175 millimeter, same thing, 1.75 meter. Okay. Number of springs are 9 and the force is given, right. The force is given P equal to 800 Newton. So, this is given. Okay. So, we want to the two pair, right, this is the two pair. So, the torque capacity for single pair. Per pair, what is the value you expect? Right. 250 by 2, right, because the two pair is given. So, this should be 125 Newton meter. So, that is clear. Okay. So now we need to understand the total spring force, clamping force, right? Total clamping force P. So what is the value you are getting, right? Should be number of springs, right? Right, number of springs into force, that is the total force, will be 9 into 800. So that should give me 7200 Newton. This will be the total acting force or clamping force acting on the clutch. This is the Newton. Okay. Yeah. So now, so we have got all the information. The case A is what will be the factor of safety when the clutch is brand new, right? That's a question. Yeah. When the clutch is new. So when the clutch is new, what will be torque equation? Remember, T equal to mu P by 3 dq small d cube d square and d small d square. Okay. So mu equal to 0.35, right? And this is 7200 divided by 3, and this is 0.25, 0.7175 cube. So can I have the value, please? What is the value you are getting? Torque should be, you should get 270.529 Newton meter. This is the value. Okay. The question is, they are asking factor of safety. What is the definition of factor of safety? Designed torque and allowable torque. Okay, right? Design torque, maximum allowable torque, right? So what is, so we have 125 Newton meter, that is your designed torque supposed to be, right? So 125 is designed and maximum is 270.529. So what is the factor of safety you are expecting now? 2.16. So that's a factor of safety when clutch is a brand new. Okay, when clutch is brand new. Now I'll do for the when clutch is, when the clutch is old, right, or worn out. So what is the torque? Mu P by 4 P, right, by 4 capital D and small d, that is it. 0.35 7200 divided by 4 into the 0.2 plus 0.25, right? Yeah, 0.25, yeah. 0.25 plus 0.175. So what is the value you are getting? This should be less or more than the will less, right? Will be less. Yeah, 267.75 Newton meter. So this is your torque, right? It's a maximum allowable torque. Maximum allowable torque you are getting. So the factor of safety, right? The factor of safety is T max by T design, right? Okay. Yeah. So 265.75 divided by 125, right? So you will get 2.14, 2.16 for the new clutch, whereas the factor of safety is reduced if the clutch is worn out, right? Worn, not worn out, worn. Okay. So we got two things. So what is the case number C? What is the problem number C? When at what thickness is worn out, so that clutch cannot perform. That means where clutch will start slip. That is what the question, right? Okay. So how are you going to do that? That one, yeah. Right. How will you do that? C. Okay. What is the way to do that? Yeah, tell me please. Already I gave information. Okay. Even though it's wearing out, right, the stiffness would be remains constant, right. Clamping force will be reduced. Okay. So where do you expect clamping force? Is it under uniform pressure theory or in uniform wear theory? That's the question. Obviously, it's uniform wear theory. That's where your the wear is happening. Okay. So when the wear is happening, we know that, yeah. So right, the torque, we know that torque equal to mu p uniform wear theory by, right, this is the equation. Yeah. So what is the value we should expect? The descent value 125 Newton meter, right? That's the value we are supposed to expect. Okay. Because of uniform wear theory. So which value would you expect to change? Your force. The force will change, right? The clamping force will change. So 0.35 into P, right? Capital P by 4. Then this should be 0.25 plus 0.175. Can you have an answer? What will be the force you are expecting? This is the total clamping force. The total clamping force P should be 3361.34 Newton. So this is the clamping force. So for one spring, per spring, okay. So it will be 3361.34 by 9. You expect 373.48 Newton. So this is the value. Okay. So the moment the force goes below 373.48 Newton, that's where the clutch will slip. Okay. When the force per spring, right, per spring will be less than 374, I am just rounding off as a 374 Newton, right, the clutch will slip. So already we got the what force, right, but when? So when do you expect the force will be reduced? At what? So how much need to be wear out from the friction lining? That's what we need to find out. Okay, that's what we need to find out. Do we know the friction lining thickness? We don't know. We don't know the friction lining thickness. Okay, but we know how much is delta, your deflection. That is clearly given, right? Delta is given. Yeah. So what we could do, we will make sure assume certain things, right? Let x equal to wear of friction lining. Okay, wear of friction lining. This much thickness has to be reduced. Okay. So the compression of a spring, right? Stiffness, right? Compression of a spring. Spring. So initial compression minus of x, how much the wearing out, that is what we need to know, because we do not know how much is going to be wearing out, right, that is what we need to know. So what is the initial compression is given? 5 mm clearly given, right, initial compression is given 5 mm. So from 5 mm certain amount of has to be wear out, right, then only the slip will occur. Okay. So 5 minus x, so this is what happening. So spring stiffness what will spring stiffness will be? When do that force what we got 374, right, 374, that is the one, right, that is a value, okay. 374 divided by 5 minus x, this is the stiffness. So much Newton millimeter, assuming that this we can have a equation number 1, okay, right. So initially 5 mm is compressed for how much spring force? 800 Newton, right, 800 Newton, okay, right. So my question is, do you think the stiffness of the spring will change? Never, it will always constant, 90% always constant, okay. Yeah, I am sure you are familiar with the spring aspect. Have you heard about open length, shut length, workable length, all those things? They are there. So however force is there, the stiffness will be there, only the deflection will change. It depends on the how much effort you are giving. That is what is happening here. Initially, my spring is compressed 5 mm for 800 Newton, right, that is what happening. But my force further reduced, when the further reduced with 374 Newton, it reduced, right. So when I have reduced, obviously what happened, my deflection will be reduced. How much is reduced, we are going to find out. But both operation, my stiffness remain constant, it won't change, yeah. So we are going to equate both, yeah. For initial condition. Initial condition means we are talking about as a new, right. So the spring, the stiffness, spring stiffness, (800 by 5). Right, so much Newton meter. Okay, so this is equation number 2. So equate both, right? Equate 1 and 2. Because stiffness should be remain constant. When you do that, can you tell me what is the answer you are getting? X equal to 2 point, yes, yeah, 2.66 so much millimeter. So right, so what is the what do you understand now, right? We do not know thickness of the friction lining, okay, but this much of the thickness need to be worn out. When this much of thickness is worn out, right, due to drop in the pressure 374 Newton, right, that is the place where the clutch cannot perform anymore. Until then it will perform, okay. So when the wear of, right, wear of friction lining, right, is more than, it should go cross beyond 2.67, okay, 2.66 millimeter, the spring force will be less than 374 Newton, okay. So at this condition, at this stage, the clutch will slip, that is it. You understand now? So why the, so now do you know that why uniform pressure, uniform wear theory is very important, right? You have to achieve that, they say torque also, right. I think I will stop now. So then next class I will discuss a couple of other type of clutch, then I will go, then we will discuss about the dynamic analysis, okay. Thank you.